Welcome to the Deep Dive, where we take your complex stack of sources, strip away the academic varnish, and pull out the knowledge nuggets you actually need. Today, we are strapping in for a deep dive into something we literally cannot escape: the foundational and hidden physics of sound and waves.
That's right. Our source material today is an excellent but, well, pretty dense summary of fundamental physics directives. It's a concentrated look at acoustics, wave transmission, and interference.
Okay.
So our mission is to guide you quickly through these concepts, clarifying exactly how sound moves, why it acts differently in, say, the ocean versus the air,
Right.
and how both humans and animals harness these complex vibrations every single day.
Okay, let's unpack this then. Let's start with the core definition. If sound is just vibration, how do physicists categorize it or measure it? What are the essential characteristics we need to define any sound?
Well, it really boils down to two things, and you can't separate them, really. We talk about the quality of the sound and the power of the sound.
Quality and power.
So the quality, what musicians call pitch, how high or low a note is, that's determined by the frequency of the wave, which is just how fast the vibration cycles.
So fast vibration means higher pitch.
Simple enough.
Exactly. And the second characteristic is the amplitude. Think of it like the height of the wave.
Yeah.
That determines the loudness or volume.
Ah, okay.
Yeah.
So a bigger wave physically means a louder sound to our ears.
Precisely. A larger amplitude wave means a louder sound.
That sets the stage for, well, our own limitations then. We all know our ears aren't perfect. If sound is just vibration, where do we draw the line on what a standard human ear can actually process?
Yeah, and that hard limit is remarkably precise, actually. For normal hearing, we perceive frequencies between 20 hertz and 20,000 hertz.
20 to 20,000, okay.
Right. Anything vibrating outside that specific window is still sound, technically, but it exists beyond our biological perception. We just can't hear it.
Which leads to the fun categories of sound we can't hear. What are the formal terms for those extremes? Okay, so frequencies below 20 hertz are classified as infrasound.
Infrasound.
Yeah, think massive rumbling vibrations, often associated with things like earthquakes or maybe the distant roar of ocean waves, that kind of thing.
Wow.
Conversely, frequencies above 20,000 hertz are ultrasound. Too high-pitched for us.
Ultrasound, right? Like bats.
Exactly. And while, age certainly lowers that upper limit for most adults, that 20 to 20,000 hertz range defines what is classified as standard audible sound, or Sessler, as it's sometimes termed in technical docs.
It's humbling, isn't it? Thinking about all that energy moving through the world that we just can't perceive.
It really is.
Now, whether it's infrasound or high-pitched whistle, that energy needs something to travel through.
It absolutely does. This is like the foundational principle of acoustics. Everyone learns it, but it's still crucial to grasp. Sound requires an elastic medium to transmit vibration.
Elastic medium.
Meaning it needs molecules to bump into each other. So solids, liquids, gases, even plasma works.
Okay. Which means the old sci-fi trope of hearing big explosions in the vacuum of space.
Totally out the window. Correct.
Yeah.
If there are no molecules, there's no sound, period. Sound cannot transmit in a vacuum.
Right.
But as soon as you give those vibrations something to travel through, the speed changes dramatically.
Yeah.
And it's based on how dense that material is.
Why is that density link so important? How does that work?
Think of it like a human wave at a stadium, maybe?
Okay, yeah.
If people are packed tightly, touching shoulders like molecules in a solid, the signal, the energy, moves from person to person almost instantly.
Right, quick transfer.
But if the people are far apart, like molecules in a gas, the signal has to cross a physical gap. That slows down the transfer.
Makes sense.
So sound generally travels faster in solids and liquids than it does in gases. The molecules are closer, more tightly bound, making the energy transfer way more efficient.
And the data from our sources on this speed comparison is really quite striking, isn't it? We're not talking small differences here.
No, not at all. It's a crucial fact for you to remember. Sound travels approximately 4 times faster in water than it does in air.
4 times.
Yeah, it's a huge jump. And in the deepest, densest parts of the ocean, the speed of sound is measured at around 1,530 meters per second. So the medium matters profoundly.
Okay, but let's stick to air for a second, our most common medium.
Yeah.
What's the main thing controlling sound speed there?
Yeah.
Like if I'm at a concert and someone screams really loud near the stage, does the loudness affect how fast I hear it?
Ah, that's a classic misconception. Loudness, or even the pitch, the frequency, it makes absolutely no difference to the speed itself.
Really?
Yeah, the speed of sound in air is almost entirely dependent on temperature.
Temperature. Okay, so if the air heats up, the sound moves faster. Why is that, physically?
Well, if the air is warmer, the molecules themselves are just moving faster, more randomly. They have more energy,
Hmm.
so they're more ready, you could say, to transmit that vibration efficiently to their neighbors when the sound wave comes through.
Interesting. Do we have numbers on that?
We do. We have concrete data points. At 0 degrees Celsius freezing, the speed of sound is defined as 330 meters per second.
Okay, 330 meters.
But warm the air up just 20 degrees Celsius, like a pleasant room temperature, and the speed increases to approximately 344 meters per second.
So not a huge jump, but definitely noticeable.
Definitely measurable, yeah.
All right, since we've established temperature controls the speed in air, what happens when a sound wave hits, I don't know, a sudden packet of colder air? Or maybe moves over a big lake where the temperatures are layered differently? Does the speed change, like mid-wave?
It absolutely does. And that change in speed is exactly what creates refraction, or, sound bending.
Sound bending.
Yeah. When sound waves pass from one temperature layer to another, say from warmer air near the ground to cooler air higher up, the part of the wave in the cooler air slows down first.
Okay.
So the wave front essentially pivots, it bends.
That must have some weird effects on how far we can hear things sometimes.
It really does. This bending is the reason why sounds from like a distant shore or maybe across a calm lake at night can sometimes be heard much more clearly than you'd expect.
Ah.
The sound waves refract, they bend back down toward the listener near the surface. It's this hidden physics altering our perception of distance.
That's fascinating. Okay, let's pivot back for a second to the sounds we can't hear, specifically ultrasound. Since we know higher frequencies vibrate faster, how have we humans learned to exploit those super high frequency waves?
Oh, ultrasound is incredibly useful, mainly because its short, high-frequency waves offer, well, remarkable detail, and they can be focused really tightly. That precision is key.
Right. So medical uses.
Oh, yeah. Medically, we use it constantly for non-invasive imaging. Like fetal screening is a big one because it's much safer than X-rays.
Echo.
But we also use the focused energy of those waves in treatments like lithotripsy. Lithotripsy. It's where high-frequency sound is used very specifically to break up hard masses like kidney stones and gallstones without surgery.
Wow, so we're basically using focused sound as a non-invasive scalpel. That's amazing.
Pretty much. But, nature figured this out long before our medical tech caught up.
Of course. Bats and dolphins, right?
Absolutely. They are the masters of harnessing ultrasound. They use these high-frequency sounds for navigation and hunting, what we call echolocation or sonar.
And they're incredibly good at it.
Unbelievably good. What's truly incredible is the level of refinement. Dolphins, for instance, can differentiate between objects that are just a few millimeters apart purely through their sound perception.
A few millimeters.
Yeah.
Just by sound.
Yep, just by sound.
Mind-blowing. Okay, moving from high frequencies to sort of the structure of sound production itself, let's talk about resonance. It seems like every object, from a wine glass to a huge bridge, has a sort of sweet spot for vibration.
That's exactly right. That's the natural frequency. Every single object has a frequency, or maybe a set of frequencies, at which it just prefers to oscillate or vibrate if you disturb it.
Okay, it's its own special vibe.
Kind of, yeah. And resonance is the phenomenon that occurs when an external force vibrates that object at precisely that same rate at its natural frequency.
And what happens when you hit that perfect match, that alignment?
Boom. The amplitude of the vibration increases dramatically. It can build up to a huge amplified vibration, a literal resounding.
Resonance, resounding.
This principle is absolutely crucial in music. It's why a tuning fork rings out loud and clear when you strike it just right.
Right.
But it's also why engineers have to be really careful about bridges and buildings, making sure wind or even footsteps don't accidentally hit a resonant frequency and cause dangerous oscillations.
Yeah, you hear stories about that. Okay, here's where it gets, for me anyway, really interesting when different waves meet up. Let's talk about beats. What is causing that weird pulsing sound, that characteristic waxing and waning of loudness, like a tremolo effect, when you listen to two instruments slightly out of tune?
Beats. Yes. That's the auditory result of interference, pure and simple.
Interference.
Yeah. When you have two sound waves that are close in frequency, but not exactly the same, they cyclically drift in and out of alignment with each other.
Okay, so they're not quite synced up.
Exactly. So sometimes their crests meet up, reinforcing each other. That's constructive interference, making the sound louder.
Louder.
But then, a fraction of a second later, they'll drift, so the crest of one wave meets the trough, the low point of the other. They cancel each other out, destructive interference, making it quiet.
Ah, so that creates the pulse. Loud, soft, loud, soft.
Precisely. That's the pulsing beat you hear.
And what I find so compelling about this is that there's a surprisingly simple math rule to figure out how fast it pulses.
There is. It's wonderfully elegant. The beat frequency, meaning the number of loud, soft pulses you actually hear per second, is simply the difference between the two source frequencies.
Just subtract them.
Just subtract the smaller from the larger. So if you have one tuning fork vibrating at 262 hertz and another nearby at 264 hertz.
Okay, 2 hertz difference.
Exactly. The beat frequency you'll hear will be exactly 2 beats, 2 pulses of loud soft every second. It's wonderfully precise physics.
That precision is just built into how waves work. Okay, now, we've talked a lot about sound waves, actual physical vibrations moving through stuff. But if you're listening to this deep dive right now over the airwaves, you're using radio waves, those are fundamentally different, aren't they?
Oh, entirely different beasts, yes. Radio waves are electromagnetic waves.
Electromagnetic. Like light.
Exactly. Same family as visible light, X-rays, microwaves, the whole spectrum. They don't need a physical medium to travel.
Ah, so they can travel in a vacuum.
They sure can. And unlike sound, they move at the speed of light much, much faster.
Okay, so how on earth do we encode sound information, which is this slow physical vibration, onto a light-speed carrier wave? That's got to be the magic of modulation, right?
Yeah.
Can you break down the difference between AM and FM radio for us?
Sure. Modulation is just the process of altering that fast carrier wave in some way to carry the slower audio signal. With AM, that stands for amplitude modulation, we change the actual power or height, the amplitude, of the electromagnetic carrier wave according to the audio signal.
Okay, so the wave gets bigger and smaller with the sound.
Right. But the frequency of that carrier wave stays constant.
Got it. And the ever-popular FM.
FM stands for frequency modulation. Now, with this method, the amplitude, the height of the carrier wave is kept constant.
Right.
But the frequency of the carrier wave is rapidly varied, wiggled back and forth slightly according to the audio signal.
I'm changing the frequency itself.
Exactly. And because FM typically operates in a much higher frequency range, standard broadcasting is what, 88 to 108 megahertz?
Right.
It generally provides a clearer signal, less prone to noise and interference than AM.
We really did cut through a lot in these sources today. We learned not just what sound is, but really why it moves the way it does and how those physical limits define so much.
Yeah, we nailed down some key numbers, too.
We did. We concerned the speed of sound at 0 degrees Celsius is at 330 meters per second. And that amazing fact, that sound moves roughly 4 times faster in water than air.
And we dissected the mechanism of beats. Right down to the math. 2 waves, just 2 hertz apart, give you 2 audible pulses every second.
Yeah, and connected those, micro-level physics facts to really tangible applications, from breaking up kidney stones with ultrasound
to understanding the critical difference between AM and FM radio that affects signal quality. The entire physical world, from the deepest ocean trenches to the air just above your head, is constantly interacting through these wave phenomena.
So wrapping up, we've clearly established that sound speed is intrinsically linked to temperature. And the physical reason sound seems to bend or refract is simply that change in speed dictated by temperature differences or moving between different materials.
Exactly. Which actually raises an important final thought for you, the listener, to consider. If sound waves are bent by those temperature differences in the air, causing sound to sometimes travel much farther, or maybe not as far as you'd expect, what everyday atmospheric phenomenon are we actually experiencing when we hear a sound unexpectedly clearly from far away? Maybe from a distant highway or across a lake on a still evening.
Ah, something to chew on. That refraction fundamentally altering how we perceive distance and sound in the world around us makes you realize the unseen physics of sound are profoundly impacting our experience all the time.
Absolutely.
It's a perfect deep dive. Thank you all for listening.